Welcome back, class. Today what we're going to be doing is going over the transformations of graphs. By the end of today's lesson, you should be able to translate graphs, both horizontally and vertically, dilate graphs based on a specific scale factor, as well as reflect graphs over both the x and the y axes, okay? So we're just going to do a little bit basic today. Later on in the year, we'll get more advanced, okay? Hopefully you guys have printed out or have received the packet that I made that goes in conjunction with this. It has a lot of the graphs on it. It'll make things a lot easier for you. If not, print it out. So first off, what does transform mean? So there's different parts of a function equations affect the properties of its graph. And we've done a little bit of this before. If we understand what part of the function controls a particular feature, we can learn how to actually transform that function. Why is this useful? Well, because we can often draw one graph from one function, and then we can use that graph to create a related function. That way, as long as you know how to draw a couple basic graphs, if you know the rules, you can create pretty much an infinite number of graphs just from those basic graphs called parent graphs that we know. So here's what we're going to do. We're going to consider three different forms. So we're going to start basic. The first one is y equals f of x plus d. All right, what happens when you just take your function and you add a specific number to it? Second one, y equals p f of x where p is greater than 0, or y equals f of q of x where q is greater than 0. So what happens here when I multiply a function by a scalar that's greater than 0? Or what happens when I take a function and multiply what's inside the function by a scalar that's greater than 0. All right. Y equals negative f of x. What happens if you put a negative sign in front of your function? And y equals f of negative x. What happens if I change the values of what's inside my function? Now these don't necessarily mean negative or positive. What they pretty much mean is you're changing opposite signs. So if your answers were positive, you make them negative, and if they were negative, you would make them positive. All right? Not too terrible, correct? So let's go. We're going to start with an investigation. You guys are going to, on your own, figure out what all this stuff means. All right, so I didn't tell you yet. Now, some of you may know this from earlier on. All right, some may not, but we will figure it out. We're going to be able to explore the transformations we can apply to y equals f of x to obtain the graph. So the first one is graphs in the form of y equals f of x plus d. You're adding or subtracting a number from your original function. So let's do an experiment to find out. So f of x is 3x. Write down what all three of these new equations would be. Go. Well, 3x plus 2. What would this one be? 3x minus 3. No. 3x plus 6. You just take your original function and you're adding or subtracting whatever the numbers are. So what do you think is going to happen here? Come on, what do you think? Let's see if you're correct. Graph y equals f of x on the other three functions of the same set of axes. Okay? So what we're going to do is what? Graph y equals 3x. So, y-intercept is 0. Rise over run, up 3 over 1. So there's your first graph. Now do your second graph. Well, what's your y-intercept here? 2. Up 3 over 1. So we're going to take a graph. Our new graph should look like that. Next graph. Minus 3. So that means our y-intercept is 1, 2, minus 3. And then up over. All right. And then we got 6. Y-intercept is 6. Up 3 over 1. Or what you can do is you can go down 3 over 1. Oh, sorry, down 3, back 1. You can do double negatives if it doesn't fit on the graph. And there's your graph. Now, what do we got going on here? What do you notice about those graphs? Tell me two things about those graphs. 1, the slopes are the same. That should be pretty obvious. And 2, all you're doing is you're moving the original graph up or down based on what you're doing there. All right? There's your investigation. Figured it out. So the original one had the origin at 0, then this one was the y-intercept was at 2, at -3, and at 6. Right? So I'd say that was a fairly easy, good start to today's lesson. All right? Next one. Now what we're going to do is we're going to repeat the same thing, but now we're doing with x cubed. Now x cubed is almost like an S curve, remember. In case you guys forget, S cubed looks like this. All right? You guys should know that by now. I shouldn't have had to tell you that, but that's the parent function. But what I want you to do before you do that is write down those three things. Right? X cubed plus 2, x cubed minus 3, and x cubed plus 6. There's nothing really to it. Graph y equals f of x. Graph the original graph. I told you it looks like an S curve. If you don't know what it is, you have 0, 0. If I plug in 1, it's 1. If I plug in 2, 2 times 2 times 2 is 8, so 2 over 8 up. All right, 3 would be 27. That doesn't fit on this graph. Now, -1, -1, -2, -8, and so on. So graph the function using three functions on the same set of axes. So, what are you going to do? We're going to take this, and what do we do with it now? Based on what we just figured out before, we're going to take it and we're going to move it up 2. So our new graph should look like what? Anyone? So what we should do then is slide it up 2. Take this one, move it up 2. Now, -3, what should we do? Take that, and we should move it down 3. Plus 6, take this original graph and, instead of the origin, move it up 6. There you go. Now describe the transformation. What kind of transformation is this? Well, you're moving the graph up d units from x cubed. So this is called actually a translation. Okay, and that's moving up or down. That's pretty easy, isn't it? Now, let me put this up there for a second, get out of your way. There you go. Next step. Now say we got a graph in the form of pf of x, where p is greater than 0, or y equals f of q of x, where q is greater than 0. Now what do we do here? You guys remember? Well, let's look. We're going to find the simplest form. So the simplest form here is, what do you do when you have the scalar out front? Anyone? What do you do when you have the scalar out front? So we're going to take this 3 and multiply our equation by 3. So it's 3 times x plus 2. But what can you do with this 3? You can distribute it. 3 times x is 3x, 3 times 2 is 6. So you get 3x plus 6. So that's our new graph. What happens when you put a 1/2 out front? You multiply the whole thing by 1/2. Distribute and distribute. Half of x is 1/2 x, half of 2 is 1. 5x plus 10. Now you're going to graph all these graphs right here, and then we're going to come up with a reason why you think that works. So first one, x plus 2. 2 is my y-intercept. Slope is 1, so I start at 2. All right, these all go up 2, 4, 6, 8, 10. Each one of these boxes vertically is 2. 1, 2, 3, 4, 5. Each one horizontally is 1. Just so you're wondering why is he starting at this, this is actually 2. So I start at 2. I go up 1, over 1, I end up here. All right. My next graph right here, I start at 6, 2, 4, 6. My slope here is 3. So I go up 1, 2, 3, and over 1. And that's my graph there. 1/2 x plus 1, so I start at 1. I go up 1, over 1, 2. So that's my graph there. And then I got 5x plus 10. I start at 10, and I go up 5 over 1, or I go down 1, 2, 3, 4, 5, and over 1. Right? And there's my graph. graph. See, pretty easy. Nothing really to it. This one could kind of be down a little bit. I kind of fudged that one a little bit, but it's okay. All right, this one's more that way. So, copy complete, we did that. For the transformation, each point becomes blank times the previous distance from the x-axis. All right, so look, this is the x-axis. If this one's 1 from there, this one is 1/2. If this one is 1 from here, this one is 3. 2. If this one's 2, this one's 10. So it becomes p times the distance. So what you're pretty much doing is taking every point, all right, and you can do it here. And every point is pretty much p times the distance from the x-axis. Good. Let's move on. Now, the key is, does any point in the graph not move? Well, if it was at 0, 0, it wouldn't move. The reason it wouldn't move at 0, 0 is, if it's at the origin, it's not going to move from the graph. Right? Next one. What happens in simplest form if we put the multiplying scalar inside? There we go. Now it's inside. So now f of 2x. So with this 2x is exchanging the x with the 2x. So 2x plus 2. All right. 1/3 x plus 2. 4x plus 2. So now I want you guys to copy these 3 graphs, plot them on there using your information, and see what you get. So first graph here, x plus 2. We're going to start at 2, and I'm just going to fix this. This graph should be more over here. It's just a little bit off. That's really what it should look like. And what should have been like this the other one too. It bothered me. I could have lied to you and told you it wasn't like this. But that's more the purple graph right there. All right, so now 2x plus 2, you start at 2. You're going to go up 2, right, over 1. 1/3 x plus 2. You're going to start at 2, right? You go up 1, rise, and you go over 3. 1, 2, 3. 4x, all right? What you do is you start at 2, you go up 4, 2, 4, and you go over 1. For the transformation, when you have your inside, okay, multiplying by something, the point becomes how many previous distance from the y-axis. Okay, so let's take an example. This point right here, we'll say is 2. You know, we're going to go with this one. This point right here is 4, 4, right? No, 4 over 6 up, right? So this right here is 4 units from the x-axis, right? Now, let's pick an easy one. This one is, red one is 2 units. All right, so the purple is 4, the red is 2. All right, what about this one? This one is, this green one is 1 unit. The red is 2. The purple is 4, and we're all doing the same y value. So let's see. If this one's 2x, and this one is 4x, right? My original value is 4. How do I get from 4 to 2 using 2? How do I get to 4 to 1 using 4? What do I do to these two numbers using this number? I divide. 4 divided by 2 is 2. 4 divided by 4 is 4. When it's 1/3, I multiply, right? So this should be 4 divided by 1/3, or 4 times 3. This blue one should be 12 units away. All right, that should be 0.312. So for the transformation, when it's on the inside of dilation, each point becomes not q times the previous distance, but the reciprocal of q, 1 over q times the reciprocal distance from the y. Does any of these points not move under the transformation? 0, 2. This point right here is not going to move under transformation. Okay? Got that? Because it's where it intersects the y-axis. So wherever it intersects the y-axis, that's the point that doesn't move. And in the other one, I should have told you too, on that specific graph, it's where it intercepts the x-axis, where it's not going to move. And I believe that point was 0, negative 2. I could be wrong, but I think that's what it was. All right, let me look. Yep, 0, negative 2. All right, part 3. Graphs in the form y equals negative f of x and y equals f of negative x. Now, in this case right here, what we're doing is we have a graph y of f of x equals 2x plus 3. What happens if you put a negative out front? Well, what does this graph become? Negative times 2x plus 3 is, distribute the negative sign, negative 2x minus 3. All right, what happens if you put the minus on the inside? What that means is you replace this x with a negative x. So that's going to be 2 times negative x plus 3, which is just negative 2x plus 3. Notice these are similar but a little different. Why don't you graph the blue, the red, and the green? Graph the 3 of them on that graph. You graphed it already? That is awesome. So 2x plus 3 means I'm going to start at 3 my y-intercept. I'm going to go up 2 over 1. So that's my original graph. This one, I'm going to start at negative 3. And I'm going to go negative 2 means down 2 over 1. All right, so what do you notice about these two graphs? They're kind of perpendicular-ish, right? They intersect, they're going in opposite directions. Start at 3. Negative 2 means down 2 over 1. All right, so these two lines also parallel. These two are parallel, so it's kind of perpendicular here. Not necessarily, though. All right, but what do you notice about it? Watch this. Original graph, right? Let's pick a point. Let's say 2, 7. Watch this. 2, 7, negative 2, negative 7. Ah. 3, 9. Negative 3, negative 9. So there is a relationship there. Ready? It says 2, 7. 2, negative 7. Oh, interesting. You see the relationship at all? I'm going to give you a hint. Go ahead. When you're doing this blue, watch this. I put a line going across. The blue and the red, don't worry about the green. Watch this. However far it is from the x, whatever you go up, you go down. Whatever you go up, you go down. Whenever you go up, you go down. When you're going with the green, whatever you do to the right, you do to the left. To the right, to the left. To the right, to the left. Reflection. So you should be seeing that. You'll see it more after this. So, right there. Original graph. First thing you want to do is negative f of x. So why don't you try that? All right, let's see how you did. There's my original graph. X cubed plus 1. Negative f of x. So negative x cubed plus 1, negative x cubed minus 1. Negative x on the inside, you're going to cube negative x. But guess what happens when you cube negative x? It stays negative x cubed. So the negative sign does not change. So now this is negative x cubed plus 1. So we graphed the first one. Now let's graph the second and the third one. So, negative x cubed minus 1. You start down at minus 1. Now negative x cubed means I'm going to take this graph and I am going to flip it. It's pretty much a reflection over the x-axis. So I'm going to start at negative 1 and I reflect it. However many distances I am from the x going up, I'm the same distance going down. Now what did we say this was? This is a reflection over the y-axis. Whatever I do to the left, I do to the right. And there's my graph. Right? And that's all there is to it. So from the investigation that we just conducted, and this is all you guys learning for yourselves, we noted that for y equals f of x, the effect of d is to translate the graph vertically through d units. So if d is greater than 0, your graph moves upwards, and if d is less than 0, your graph moves downward. That was the first part. Part 2, if y equals p f of x and p is greater than 0, it is a vertical stretch, meaning you're stretching it up and down of f of x with a, now dilation is another word for stretch, just so you guys know. And it has a scale factor of p. Alright, so that's your scale factor. So if p is greater than 0, you're making your figure larger. What do you think happens if p is less than 0? Your figure shrinks. Each point becomes p times the previous distance from the x-axis. Okay, so that's just shrinking it vertically. If p is greater than 1, the points move further away from the x-axis, as I just said. Oh, sorry, you won't be negative. You can't have negative because your dilation will never be negative. It's always from 0 there. But if it's bigger than 1, that means you can think of 1 as like 100%. You're going to get larger. You can think of between 0 and 1 as like multiplying it or having 0 to 100% of something. So if you have like 50% of something, 0.5, that's like half, right? If you have 40% of something, that's 40 over 100, which is 2/5 of something. So it's getting smaller. So if p is between 0 and 1, the points move closer to the x-axis. Now points on the x-axis actually do not do what? No matter what you multiply a point on the x-axis by, it's not going to move. Now the reason you can't have 0 is if you multiply by something by 0, it just disappears, and your answer is not going to disappear. 0% of something is nothing. All right. Now the reason if you multiply by 1, what happens? 100% of something is the same. It stays the same. All right. If y equals f of q of x and q is greater than 0, so the number inside here is greater than 0, a horizontal stretch with a scale factor of 1 over q. This is the third part we did. All right. Sorry, the second part. Each point becomes 1 over q times the previous distance from the, not the x-axis, but the y-axis. Right. Now, as before, if q is greater than 1, greater than 100%, your answer is going to move closer to the y-axis. The reason it's moving closer is 1 over a larger number actually makes that answer get smaller, right? Because 1 over 10 is a larger number than 1 over 100. So the larger number you get, right, the closer it gets to the x-axis, or y-axis, sorry. Too many axes. So if it's between 0 and 1, now 1 divided by a number between 0 and 1 is pretty much 1 divided by a fraction. So that means your number is going to actually, your number in reality gets larger. So it's going to be moving further away from the y-axis, okay? You can think of it about this way. If I did, and maybe this is just for me, 1 divided by 3, say my q is 3, your answer is 1/3 the distance from the y-axis. But say q was, I don't know, 1/4. You would do 1 divided by 1/4, which is the same as 1 times the reciprocal, which is 4 for 1, which is 4. So it's 4 times the distance away. I don't know if that helps you at all. Hopefully it does. But it would be something that would help me. Whoop! But you don't need to copy it. All right, so the points on the y-axis obviously do not move. Last step, step 3. If you have a negative in front of your whole function, it is a reflection, and it's a reflection in the x-axis. That means you're going to reflect it over the x-axis. All right, so you have your 2 axes. You have your x, you have your y. This one, you're reflecting it over here. So if your answer's up here, it moves down there. If the function is negative on the inside, so f of negative x is also a reflection, but this time in the y-axis. All right, so what that means is, if I have a figure over here, say I have a y over here, I reflect it over here. All right, that's it. That is all the rules we're going to be using, and you guys discover them all yourself. Hopefully. Now you can do examples. The rest of the time is examples. That's the hard part, explaining everything. So, first one. Consider the graph of y equals f of x alongside. Draw the following graphs. Y equals f of x plus 2. Y equals f of x minus 3. So we know these are going to be vertical stretches because we're adding things afterwards. So the way this works is very simple. I'm going to take all these points and move them which way? You're going to move them up, and how many up? 2. So f of x translates 2 units upward. So I'm going to take each one of these points that is a good point and move it up. So I'm going to take this, move it up 2, move it up 2 because you got 1, 2, and my new figure slides up, 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 and there's my answer. This was originally 2, it moves to 4. This was originally negative 1, moves to 1, negative 1 moves to 1, negative 3 moves to negative 1, negative 1 moves to 1. And notice your figure stays the same. All right? It's called isometry. All right? That means that even though we're changing our figure, it remains the same. Okay? B, negative 3. All right, in this problem right here, you should be moving all your things what? Down 3. 3 units downward. So I'm going to take each one of these points and slide it down 3. It goes from 2 to negative 1. It goes from negative 1 to negative 4. Negative 1 to negative 4. Negative 1 to negative 4. Negative 3 to negative 6. And that's my answer. Notice figure remains the same. All you're doing is sliding it downwards. I know I'm going a little slow here. I know you guys are smart in this, but you got to start slowing. So now what you guys do, problem number 1 on your own. All right, you're done? That is awesome. You guys are really quick at this stuff. First thing you're going to do, you notice the 5 here. So that means you're going to move it up 5. All right? So this point goes from 0 to 5. From negative 4 to 1, from negative 3 to 2, negative 2 to 3, and I'm just going to slide upwards. There's really nothing to explain, that's it. Same figure, minus 2. I'm going to take all these things and I'm going to move them down 2. All right? 0 to negative 2, negative 2 to negative 4, negative 5 to negative 7, and so on. Now you may say, how come I'm not moving it horizontal? Well, in this chapter, for some reason, they don't go over horizontal movements, but that would be if you were adding or subtracting things inside your f of x. So, for instance, if this was f of x plus a number, you would actually move it to the left. If it was f of x minus a number, you would actually move it to the right. I guess we're going to do that later on. Just got to hold tight with me for that. I just do whatever the book says in the order the book says. All right, so now I want you guys to try problem number 2. And also, if you need to print out the grids, there's printable grids right in the book where you can just click on it and print it out. Or like I said, you can go right on my Canvas page and print out the packets that I made for you. Spent a lot of time on those guys. All right, let's go with this. G of x plus 1. We're going to move every point up 1. Slide all our points up 1. This point goes from, what's this, 4 to 5, 2 to 3, 3 to 4, 0 to 1, and so on. Minus 3 means all the figures are going to move down 3. All right? 1, 2, 3. And the figure remains the same. And you don't have to draw these arrows. I'm just showing you exactly what I'm doing. Okay. Boom! Now, we're going to go backwards. Write g of x in terms of f of x. So the way this works is fairly simple. G of x is my red graph right here. F of x is my blue graph. So g of x is the top graph. Now when you're writing in terms of f of x, g of x equals, what am I doing to f of x to get it to be g of x? I am adding 3, right? So g of x equals f of x plus 3. And that's it. That's all there is to it. Ready for the next one? Boom! Find the equation resulting in the graph. So now you're creating a new graph called g of x. Now you're going to take these original equations, you're going to move it 4 units down, move this one 3 units up, and move this one 6 units down. I know we didn't go over this, but you should be able to figure this out. So, when you are moving an equation, all you're doing is taking the equation and adding whatever this is. Now, downwards would be a negative number. So I take my original equation, f of x, and I'm going to subtract 4. Down minus, up plus. So, 2x plus 3, minus 4. 3 minus 4, 2x minus 1. And that's all there is to it. So why don't you work on B and D? All right, f of x plus 3, so this equation plus 3, well, negative 7 plus 3 is negative 4. Negative x squared plus 5x minus 4. Pretty easy to me. This one right here, 6 units down, meaning you're going to take f of x and you're going to subtract 6. So you're going to take this whole thing right here, subtract 6 from it. 2 minus 6 is negative 4. G of x equals x cubed minus 4 minus 1 over x. Notice these do not change because there's nothing to combine them with. I told you, the setup was going to take all the time. The rest of this stuff, pretty easy. Okay. All right, number 5. Now we're going to sketch 1 over x using any technology if necessary, meaning if you want to go back to your book and use the graphing emulator they have there, you're more than welcome to, the graphing package, sorry. So, I know I can graph this. X cannot equal 0, so there's an asymptote there. All right, your answer is never going to be 0 because you have no value at top. And I know for a fact, I remember this is the rational equation. It looks something like this: 1, 1, negative 1, negative 1. And then as you go more towards infinity, you approach 0. As you get closer to 0, you approach negative infinity this way, and the same over there. So now what we're going to do is we're going to translate k upwards to produce g of x. So suppose f of x is translated k units upward to produce g of x. What do you think that function would be? Pretty simple. It'd just be g of x would be f of x plus k. So what does f of x equal? 1 over x plus k. That's what the equation would be. What would your new horizontal asymptote be? Right here it's 0. So if I add k to my answer, what would my horizontal asymptote be? Well, f of x is 0, right? That's what you're trying to solve for, correct? So my new horizontal asymptote would still be at f of x is 0. Problem number 11. What we're going to do is we're going to do our dilations, okay? Dilations, also fairly simple, shouldn't give you too much trouble. In the first one, you're going to multiply your thing by 3, okay? So when you have a scale factor of 3 out front, what did we say that involves? Are we going to make our answer larger or make our answer smaller? What do you think? Well, let's see. It's a vertical stretch, y equals f of x, with a scale factor of 3. All right? So, vertical means up and down. So this stays here. We're not going to stretch it horizontally at all. So it's not going to smush or anything. So watch what happens. I multiply everything by 3. 0 times 3 is 0. 0, 0. So these stay. Anything on the x-axis stays on the x-axis. However, since this is 1, 1 times 3 is 3. Negative 1 times 3, or negative 2 times 3 is negative 6. So this is your stretch. All right? That's pretty terrible, right? All right, now what happens when it's on the inside? Well, when it is on the inside, what you're doing here is what? Oh, that last answer, I said f of x is 0. It should have said f of x is k. I don't know why I said 0 there. where the new asymptote's going to be. That was 5b2. F of x was k. I'm going to clean up all this stuff. All right, so this one, your answer is going to be stretched by a scale factor of 1 over the number next to x, so 1 over 2. So that means I'm going to shrink this. So these vertically remain the same. This is going to stay right here. This is going to stay at 1. But this point goes from 4, half of 4 is 2. Half of negative 4 is negative 2. So I'm going to shrink, and then half of negative 1 is 1. Half of 2 is 1. Sorry, half of negative 2 is 1. Half of 2 is 1. So it shrinks our figure. And 0 stays 0. The original stays the same. All right. Ready to do some on your own? Sure. If the scale factor is greater than 1, your graph is elongated for this one. If the scale factor is greater than 1 here, it's shrunk. So if the scale factor is between 0 and 1, the graph is compressed. For A. For B, if the scale factor is greater than, this turns your scale factor less than 1, so that's why you're compressing it. So this number in here, this Q actually isn't your scale factor. 1 over Q is your scale factor. So these rules stay true for this. Got it? Awesome. Ready for the next one? I want you guys to try this one right here. Consider the graphs of y equals f of x alongside. So the first one, we're multiplying it by 2. All right, so it's a vertical stretch with a scale factor of 2. That means you're going to multiply every number by 2. Since all the numbers are positive, they're just going to go up. So this stays. This goes from 2 to 4. This goes from 3 to 6. There you go. This goes from 3 to 6. A nice little scale. This one, the 3 is on the inside, so we're actually going to get smaller. 1 over Q is 1 over 3, so a horizontal stretch with a scale factor of 1/3. 1/3 is obviously between 0 and 1, so we're going to be shrinking this. These stay at the same heights, but this goes from 1/3 of 3 is 1, 1/3 of 6 is 2, stays, 1/3 of negative 3 is negative 1, 1/3 of negative 6 is negative 2. So we shrink this little guy, get it back. Boom! Problem number 7. All right, this one right here. 1/3, smaller than 1, greater than 0. So all these figures are going to stretch with a scale factor of 1/3. So they get 1/3 smaller, 1/3 of negative 3, and like I said, this is vertically. So this point stays, because they're already on the axis. Any point that's at 3 goes to 1, negative 3 goes to negative 1, and negative 5 goes to like negative 5/3 or negative 1 and 2/3. There's your answer. You know they don't have to exactly land on the points as whole numbers. This right here, inside is a horizontal stretch. 1 over 1/2 is actually 2, so it's a scale factor of 2. So all these figures are going to go 2 outward. Negative 3 times 2 is negative 6. Negative 4, negative 2, stays at 0. That point gets 2, that point goes to 4, and that point goes to 6. And there you go. Nice and easy, right? All right, I think you're ready for problem number 8. Now, what you're going to do is do this backwards. You're going to write g in terms of f of x. So this is my original question. What is my new equation? Well, my new equation here, as you can see, this looks like a vertical dilation. So originally it went down 1 here, so it's 2 away. This was 1.5, now it's 3. This is 2, now it's 4 away. So I am doubling the amount I'm going away. So what happens here is I'm getting larger, it's doubling, so that's a 2. So g of x equals 2 times f of x. All right? That one, everything vertically stays the same, but it looks like horizontally I'm switching. So originally I was here with these points here at 1s, and now they're at 1, 2, 3. Okay, originally this point was at 1.5, 1.5-ish, and now it's at 1.5, 3, 4.5. Okay, so what am I multiplying these by? I'm multiplying it by 3. It has a scale factor of 3. Now since the scale factor is 3, I don't put, and it's going to be on the inside is not going to be 3. The inside is going to be 1 over the scale factor. So it's going to be 1/3. F of x is 1/3 x. Okay. Let's move to problem 9. A linear function with a gradient m is vertically stretched with a scale factor of c. So you're stretching it up and down with a scale factor of c. What's the new gradient? Gradient is another word for slope. So if my original slope is m and I stretch it vertically, what would my new slope be? What do you think? It's originally m, I'm moving it as a scale factor of c. Well, it would just be c times m, cm. This is the new gradient. Right? And then you might have a b here and multiply them both by b, but then this would just be plus cb. But we only cared about the gradient, and the gradient was cm. All right? That's it. That was an easy one. That was a waste of space right there. All right, number 10. What you're going to do here is you are going to, just as we did before, you have these original equations. You're going to vertically and horizontally stretch them by those scale factors. I believe we have 14 questions here, so we're almost done. After this, we'll be like 2/3 done. All right, so the first one, vertically stretching. When you vertically stretch something, you multiply the whole function by that much. So I'm going to take 2 and multiply it by f of x. 2 times x squared plus 2, distribute the 2. 2x squared plus 4. Boom. Horizontally is 1 over the scale factor, so you're going to multiply 1/3, and you're just multiplying it by this x. So f of 1/3 x, so 5 minus 3 times 1/3 x. 1/3 of 3 is 1, so 5 minus 3 x. Sorry, 5 minus 3 over 3x, or 5 minus 1 over 1x, or 5 minus x. Whew. Ready for the next one? Of course you are. Vertically, so you're going to multiply everything by 1/4. 1/4 of x cubed plus 8x squared minus 2. Well, this just becomes, distribute this to all 3 of these. 1/4 x cubed plus 8 over 4 is 2x squared. 2 over 4 is minus 1/2. And there you go. All right, last one. Horizontally, so that's going to be your f of 1 over 1/2, so f of 2x. You're going to put 2x in for both x's. So this is 2 times 2x squared plus 2x minus 3. All right? 2x squared is 2x times 2x is 4x squared. So it's 2 times 4x squared is 8x squared plus 2x minus 3. All right? Last type is the reflection. So, consider the graph of y equals f of x alongside on separate axes. Draw the graph. So, first one. Y equals negative f of x. If the negative is on the outside, you are going to reflect over the x-axis. What that means is, anything on the x-axis stays on the x-axis. Since this is about 1 a little bit away, it goes 1 a little bit down. Up, down, up 2, down 2, all right? up 4, down 4. And it's a direct reflection. All right. B. What do you think we do there? What do you think? Reflection of the y-axis. The y-axis is the axis that goes up and down. That guy right there. So, since this is 1, 2, 3 to the left, I'm going to move 1, 2, 3 to the right. Stays on here. Since this is 1, 2, 3 to the right, I move 1, 2, 3 to the left. And my new graph looks like that. Yes, they can cross each other. Yes, they can touch each other. Now you're going to attempt some on your own. So I want you guys to attempt problem number 11. You're going to do negative f of x and f of negative x on the same graph. Now what happens if I mix them up? Well, you're 100% wrong. Don't mix them up. All right, so the first one, negative f of x, is in the x-axis. So we're reflecting it over this x-axis. That means if I go up 3 here, I go down 3, up 3, down 3, up 2, down 2. Down 1, up 1, up 2, down 1. And there is my graph. Just pick a couple good points and connect. This one's a reflection over the inside is the y-axis. Whatever I do to the left. Left 1, right 1. Left 3, right 3. Right 1, left 1. Right 3, left 3. Right 2, left 2. And they keep the same heights. There's the answer. See? Pretty simple, isn't it? All right, so you're going to do another set. Copy the graphs and sketch the graphs on the same axis. Now you're just doing find y equals, you don't need all the special stuff, y equals negative f of x. So what does y equals negative f of x mean? That means you are going to reflect over what axis? That's the case. Your x-axis, so they're all being reflected over the x. So you're just sketching. Since this starts low and goes up, start pretty close here, and go down. Same thing, over the x-axis. So this is a parabola going up, this obviously is going to be a parabola going down. I would just pick like a main point, like, okay, this is down about this much, put a point up about this much, and then have the arrows go down. Make sure they do pass through the same points, they do have the same x-intercepts. All right, lastly, this one, pick some points. You want to make it easy, be like, okay, I know for a fact that there's going to be a point here, 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 because if it's on the x-axis, it stays there. And then go like this, like, okay, this point's a little bit up here, I'm going to put one a little bit down here. Go down a little bit, okay, go up a little bit, up a little bit, go down a little bit, down a little bit, okay, go up a little bit, and then just connect all your stuff. And then when you connect all your stuff, look at that, all by the eye. Okay, great. All right, problem number 13. 2 more to go. Now we're doing this f of negative x. So this one is reflected on the y-axis. So draw a line down my y-axis. Since this goes to the right one, I go to the left one. All right, since I go a little bit here, a little bit here. Pick like 3 points. Here, here, all right, move this one here. Oh, this one's really far over there. There we go, I got my points. And there's my graph. Let's see how close it came. Oh, it came pretty close. Just pick a couple quick points to sketch. All right, this one, once again, the y-axis. All right, since I'm going about here, I go, okay, put a point here. I know I'm gonna cross the y-axis. All right, put one there, and then draw your graph. See? I was off a little bit there, but you guys get the point. This one, what do we do with this? First thing you have to do is you have to not only move the graph, you're going to move the asymptotes as well. Because this was negative 2, this was 2, and this is 1. So now I'm going to put a new asymptote here at negative 2. and that asymptote stays the same because it's horizontal. All right, so I'm going to reflect it. I reflect the asymptote, and then I'm going to reflect this piece, and then this one I reflect out. All right. Last question. It says, find the equation in the resulting graph if you have A, B, C, and D. So what you're doing now is you're reflecting these graphs, and you're going to see what answer you get. This wasn't too bad. Under an hour. This is about 3 days. So first one, reflected in the x-axis. All right, that is your negative f of x. So what I do is I take this whole equation and I multiply it by -1. So negative 5x plus 7, negative 5x minus 7. All right? Got it? Next one. If it's reflected in the y-axis, it's f of negative x. 2 to the negative x, which is your answer. That's it. Next one. You're reflecting it in the x, negative f of x. So I take a -1 and I multiply it by this whole function. Negative 2x squared plus 1, negative 2x squared minus 1. I like that. Last problem. Y-axis, f of negative x. So I'm going to put a negative x in for 1, 2, 3, 4 pieces. Negative x to the 4th minus 2, negative x to the 3rd minus 3, negative x squared plus 5 negative x minus 7. Now watch. Negative x to the 4th is 4 negatives is a positive. Minus negative x to the 3rd. Negative x to the 3rd is negative times a negative. So that means this becomes positive 2x to the 3rd. Negative x squared is positive, but it becomes a minus 3x squared minus 5x minus 7. And there you go. You just count the negatives. 4 negatives even. 1 plus 3 is 4 negatives even, because they're both positive. 1, 2, 3 negatives is a odd, negative. 1 negative odd number, negative, and then 1 is not. Then we're done. So, hopefully today, what you learned how to do was transform graphs. We did it very basically. We will get more into more difficult stuff later on this year. All right, so we just did, we translated the graphs pretty much vertically. I don't even think we really did horizontally. We'll do that later on. We dilated based on a scale factor that was inside and outside. So we found out P and Q, which is the scale factor is 1 over Q. And then reflected graphs over the X and Y axis, okay? Obviously, there's many more things to do with this that we will add on over the year. But for now, you get a basic gist of the transformation. Stuff you all did in geometry class, so you should be experts at already. Anyway, all right, so if you have any questions, you know where to get me. And until next time, have a good day.